Chapter 14, we're looking at acids and bases and the equilibrium between them. We're going to start out first of all by looking at the characteristics of acids and the characteristics of bases and compare them as we go through. We're going to start out with acids and the characteristics of acid. One of the characteristics of acid, they have a low pH. pH is the measure for how acidic or how basic something is. pH of 7 is neutral. Another characteristic of acids is when you use an acid indicator called litmus, which usually is put into paper, it will turn the paper red. So acids turn litmus red. Foods that are acidic tend to taste sour. So any acids that you taste are going to taste sour, such as lemons, citric foods, limes. Those are all acidic fruits. And a final characteristic of acids is when you combine an acid with a metal, you end up getting hydrogen gas produced. If we look at bases and the corresponding characteristics, bases have a high pH. Low and high, again, tend to be relative to a pH of 7, which is neutral right in the middle. So pHs bigger than, higher than 7 are basic in nature. pHs that are less than 7 are going to be acidic in nature. Turning to litmus again, that's the paper that changes color, whether it's an acid or a base. Litmus in the presence of base will turn blue. There are foods that are basic, and basic foods tend to taste bitter. Caffeine, seltzer water, those are both examples of bases that are bitter. And the final characteristic for bases, and you want to try and avoid this for the most part, is if you spill a base on you, it feels slippery. The reason bases feel slippery is they react with the lipids that form the cell membranes of your skin and start dissolving it. And when bases come in the presence of lipids or fats, they react chemically, and that essentially is the basis for forming soap. So essentially what you're doing is turning your skin into a layer of soap, which is why when you run your fingers together, when you've spilled a base on them, they feel slippery. There are many theories we use to explain the nature of bases, and we're going to look at a number of them. They start out relatively specific, the older ones, and then as we become more recent in the theories, they become much broader based and much more inclusive in what they count for acids and bases. We're going to start with Arrhenius first of all, and with each of these theories, we're going to look at how they defined acids and how they defined bases. Arrhenius defined acids as substances that produce hydrogen ions. He defined bases as substances that produce hydroxide ions. And this definition for acids and bases works well for most of the compounds we're going to work with. Any of the common acids that we have dealt with have hydrogen ions that are liberated when they serve as acids. And most of the bases that we will work with produce hydroxide when they are dissolved in water. The problem comes along when we look at a compound like ammonia. Ammonia is basic, but if you look at the formula of the compound, there's no hydroxide present in the formula. So how do we explain the nature of that compound as being basic? Arrhenius's theory can't do it for us. That leads us to the next guy's theory. Actually, it's two fellows, Bronsted and Lowry. Bronsted and Lowry defined acids and bases a little bit differently. Bronsted and Lowry described acids as being proton donors. And if you think about it, a hydrogen ion really is just a proton, because when you rip an electron off of a hydrogen, all you have left is a proton. So Bronsted-Lowry's definition of an acid is pretty much the same as Arrhenius' definition. In both cases, we're generating a proton or a hydrogen ion. The difference comes when we're talking about bases. Bronsted and Lowry defined bases as being proton acceptors. So we have a broader definition here. It's not so much for bases what they can create, it's what they can accept. And in this case, bases can accept a proton. So it works for all of our common acids and bases, and it works also for acids and bases that we wouldn't normally think of as being that way. The next thing we're going to take a look at is something called the hydration or the ionization of an acid. And when it's put in water, what's actually formed is a hydronium ion. Hydronium ion is H3O+, and in an acidic solution, we don't have bare protons running around. The bare proton will join up with a water molecule and adds its positive charge to the water molecule. We have 3 hydrogens attached now. That's actually what's present in the solution, not the bare protons. So if we look at this reaction of hydrochloric acid or hydrogen chloride as a gas, if we bubble it into water, pure water as a liquid, what we get is the hydronium ions, which are the H3O+ ions, and the chloride ions. This is an equilibrium, so there are going to be some hydrogen ions and some chloride ions that recombine and go back to form gaseous hydrogen chloride, but not a lot. Now, chemists tend to write hydronium ions when they have to. They are much more likely to write and represent them as H+ and understand that what is present in the solution is the hydronium ion, not the hydrogen ion. Now, if we look at how do we write a generalized equation for an acid in water dissociating, HA stands for any acid. The hydrogen ion is what's liberated and joins the water molecule to form the hydronium ion. The A- is the anion. So here's our generalized reaction where the HA is equivalent to the hydrogen chloride in the previous reaction. And hydronium ion is the same. A- then is the equivalent to our chloride ion in the previous reaction. And when we talk about equilibria, it's much easier to see it when we're talking about it as a generalized reaction. One of the things we're going to take a look at now is with Bronsted and Lowry, we don't always have an acid plus a base neutralizing. We sometimes will have an acid reacting with a base and we get conjugate. A conjugate essentially is a product that behaves as an acid or a base but is not the primary acid or the base. And when we have a conjugate acid-base reaction, what we have going on is a contest for the hydrogen ion. We can either have the acid on the reactant side that has a stronger pull for that hydrogen ion and so hangs on to it, or we have the hydronium ion that has a stronger pull for the hydrogen ion and hangs on to it. And so the way that we're going to look at these reactions is we're going to label them as acids and bases, because remember, the acid's the proton donor, the base is a proton acceptor, according to Bronsted and Lowry. And then for our conjugates, we'll have a conjugate acid and a conjugate base, and those are our products. So if we look at this overall reaction, HA is our acid because it can give up a hydrogen ion, donate it. Water then becomes our base by this definition because it can accept that proton. In fact, it does to form the hydronium ion. So that which behaves as an acid, that which has accepted and has joined with a hydrogen ion as a product, becomes our conjugate acid. And the anion from our original acid becomes what we call the conjugate base. This conjugate acid-base reaction is produced and occurs in equilibrium. When we have a conjugate acid-base reaction, the stronger acid is the one that gets to hang on to the hydrogen ion. So in this particular reaction, we're going to look at the concentration of our original acid, HA. We're going to look at the concentration of our hydronium ion. Whichever is larger ends up being the stronger acid. So if we look at our original reaction, we have two conjugate acid-base pairs. We have an acid-base pair of our acid and we have a conjugate acid and its base. So our first pair is our acid conjugate base, and then we have our conjugate acid and base. They're usually referred to as a conjugate acid-base pair. Now we get into the equilibrium. So there's the equilibrium expression. We have the hydronium ion times the anion in the numerator. We have the concentration of the acid in the denominator. What's missing? Well, water doesn't get included, remember, because water is a pure liquid. So it's really not missing because it's not supposed to be there. Ka, new equilibrium constant, is called the acid dissociation constant.